So for today, we want to talk about model of execution still, and specifically we want to talk about the heap in heap memory. So we have two different types of memory. Stack and heap. We've talked about stack so far, and we know what stack is. We've already went through that quite a bit, and we will revisit some stack just as we talk about heap. That's going to naturally come up. But let's talk about this different form of memory called the stack, and specifically references is going to be the big keyword that pops up a lot when we talk about heap space. So for this task, the testing is actually the big part of this task. There's one specific test incorrect solution that you need to write a test for that's going to test your understanding of references and your handling of references. So let's talk about this. Let's set up the stage first. We want to write a class named sale, which is going to take a percentage off in its constructor. This constructor parameter has to be named %off, and it has to be a var. This is something that I'm going to access during testing. So it is a named variable, meaning it's fair game for testing. I'm going to change this %off value after creating a sale. And you should do the same thing in your testing. You'll have to do the same thing to get this one particular incorrect solution to be marked as incorrect. Create a sale, attach it to a sale testing item, and change the %off afterwards. And that change should cascade through your whole program because everything's using references. And so we want to understand how that works today. An update price, which applies the sale to an item. So if I have an item that's $100 and I create a sale with 20 in its constructor, 20% off, and I call update price on 100, that should return 80. It should apply the sale to the input price. So next, we need an item to be able to test this. We have the item class, but just the way that we're going to structure the project moving forward in the later lecture tasks, we actually can't use the item class to test this sale functionality. It's going to break when we start learning inheritance if we do that. So we have a special type of item that we're going to create, a separate class, sale testing item, which is going to be an item that helps us test this sale functionality. Its constructor is the same thing as item that you created on Monday. And it's going to have two other methods. You don't need any other methods from the item class. We only need these two. Add sale, which takes a reference to a sale object and stores it for later. And then a price method, which returns the price of the item, which is the price from the constructor with every sale that was added with add sale applied to it. So as we add sales to this item, the item has this base price that it has from the constructor, which is never going to change. And when we call the price method, it should look up that base price, apply all the sales to it by calling update price, and then returning that sale price for the item. A few things to note. Items can have multiple sales, so you have to have a data structure to store all these sales. And a sale can update after it was attached to an item. So we're going to create a sale testing item in the overall test, create a sale testing item, apply multiple sales to that sale testing item using add sale and creating new sales, and then taking one of those sales, a reference to one of those sales, and changing its %off after it's been attached to an item, and then checking the sale price of the item, and that item's price should reflect the new updated %off for that sale. To understand how all that works, we got to talk about references and heap space. So let's talk about that. Oh, first, there is no new lecture task for Friday's lecture. This task might be tough to really wrap your head around after today's lecture. Friday's lecture is all about reinforcing the material introduced in today's lecture. So this is pretty much a 2-lecture task. So to really understand what's going on with these references and heap space, it's going to take 2 lectures to talk about, at least. You know, it's a concept that takes some time, takes some digestion time for our brains to really think about it. Take a shot every time he says sale. Oh, and reference. If you want to do a drinking game today, reference is the word. Every time I say reference, take a shot. You'll be completely wasted at the end of this lecture. I'm going to say that word so many times. So, good luck, Smeech. We talked about stack memory, and I'm not going to reiterate and do a recap of all of stack memory. But when we did stack memory, we only can talk about these variable types, these types. These are what we call primitive types. The word primitive comes from Java and the JVM. These are objects in Scala, and I'm going to say all objects are stored in heap memory is kind of the truth, but all other objects other than these ones are stored in heap memory, because these ones, after the compiler gets a hold of our Scala objects, it's going to convert these into the JVM primitive types of these values. So these behave a little differently. They actually go on the stack like we've seen so far in the class. And I was careful not to use anything other than these in those examples. I used double and int, I think exclusively, just double and int for those. I never used a string when we were talking about the stack, because string, not in this list. This is a comprehensive list of everything that's going to be stored directly on the stack. String is not included in there. String is something that goes on the heap. Everything else goes on the heap, goes in heap memory. Everything else. And a little caveat, just for those of you interested, this is a little bit of a simplified view. Modern compilers are so advanced that they have all kinds of crazy optimizations built in, that they do lots of cool stuff. So some things that should be in the heap based on the concept of stack and heap are actually going to end up on the stack just because the compiler optimized it and said that'll be faster. We're going to ignore the optimizations. It's really interesting stuff for you to learn someday. But we're going to stick with this little bit simplified view, and we're going to assume that the compiler sticks to the concepts. The concept of a stack keeps these on the stack, everything else in the heap. So we're going to keep that simple. So if you have an interview question, which you'll have questions like this for this learning objective, that says, if I create a variable of type int, does that go on the stack or the heap? It's going on the stack. If I create a variable of type list, does that go on the stack or the heap? It goes on the heap. These go on the stack. Everything else goes on the heap. If one of these, and I'll talk about this probably more in depth Friday, I'll remind you of this, but any of these values that are part of an object that's stored on the heap, that's going to be stored on the heap. There are ways to get doubles and ints on the heap. Just make them part of an object that's stored on the heap. Are there no TAs in chat today? There might be. There might not be. Ren the TA actually has an internet outage, so unfortunately he can't make it. Yeah, Mike is hiding. There's probably someone lurking, just waiting for you. They're honeypotting you, waiting for you to get out of control, and then they're gonna hit you. They're gonna hit you with the bans. All right, so let's talk about heap. The stack is very structured, and to motivate heap, I'm going to talk about stack. The stack is very structured. What if we want more dynamic memory? So what if I have this program which creates a list which needs to be stored? We know from the previous slide that that's going to be stored on the heap, but we don't know what the heap is yet. So let's try to do this with what we know, with just the stack. 2 TAs in chat. All right. I think I gotta mod some more TAs. And then we want to put some more variables on the stack, and then modify that list. Update this list variable to store a list with an extra element in it. So to do that, let's look at a wrong way to do that. All this red text and these crossouts. This is a bad example. This is not how things actually work. So don't use these slides as reference. I tried to give you enough warning signs. Don't use these slides as reference with the red headings. This is not how the heap works. So the heap, so with just the stack, without the heap, how would we do this with the stack? Well, we're going to put our command line arguments on the stack in this main method stack frame. We're going to create a variable named list and assign it this object list of 2, 3. So here, instead of just having enough space to store one int, and I'm kind of hand wavy with how much storage each value takes, but enough storage for one int right here, and enough storage for space for another int here. So we have 2 ints stored on the stack in this list variable. This is how we would do it with what we know so far. We move on through our program. We put X and Y on the stack. We're all familiar with that. And then we get to this scary little line. How do we do this using what we have set up? So we want list. So we're creating a brand new list with the values 1, 2, 3 and reassigning it to the variable of name list. Hey, Ashley, what's up? and reassigning it to the variable named list. How do we do this? How do we do this with what we know about the stack? Let's explore our options and talk about how we might approach this. Let's take option 1. Let's just add it. Let's just update the list where it is in the stack. So for this, we need room for another int. So we're going to have to make space. So we're going to have to take x. What we could do is take x and y and move them down the stack to make room. Move the list values 2 and 3 down the stack to make room, and then add the value 1 as the first value in the list. But this is horrible. It's too slow. You have to copy everything in the stack, move everything down to make space, and then add that value to the stack where we made that space. It also violates LIFO. It really isn't a stack anymore. We're treating the stack as an array and just moving things around at will. We're not using a last in, first out approach with this. So let's explore another option. That one's bad. We don't like that. So let's take a look at another option. Well, let's move the list to the bottom of the stack. Let's respect some LIFO there and just add the new list to the bottom of the stack and create that new list, add it to the bottom, and have values 1, 2, 3 down here. And then we have to delete the other value, the other list, because we're in the same block. We're trying to create two variables of name list in the same block. We can't do that, so let's delete the other list. Well, once we delete that, we first leave a gap in the stack, and we also violate LIFO again, because we just removed something from the stack that was not the last element that was added to it. So we still violated LIFO. We have its gap in the stack, and it's pretty slow because every time we change the stack, we change the list, we have to copy the entire thing. That's a pain. So let's not do that either. That's horrible. Let's not do that. So let's look at our good option. Nice green text so you know that this is the one we want to talk about. This is the one we're actually going to do, is we're going to introduce heap space and allocate memory in the heap, which is memory that's separate from the stack. So we have the stack, and we know how that works. It works like a stack data structure, LIFO ordering. Hey, you guys have the same question that you keep asking. I'll take a few seconds. If you pass the interview and quiz already, if you have ones in Autolab for both, you don't have to go to lab this week. You only have to go to lab if you have a 0 for one or both of those. And if you go to lab, you say you got a 1 on the interview and a 0 on the quiz, you're only taking the quiz in lab. So quickly, just because I saw that question like 5 times so far already. Those type of questions are best for before lecture. Just show up 5 minutes before and ask. So we're going to use heap space, and I'll use heap space and heap memory interchangeably. If I say heap memory, heap space, anything with the word heap, I'm talking about the same thing. So the heap is going to be extra memory that's separate from the stack. Now, when we create these in heap space, we have a lot more flexibility in what we do. And when we create this list in the heap, we're going to have this list 2, which refers to 3, and we'll get into all the details of how lists work and all the way down in Learning Objective 4. But we're going to have the values 2 and 3. And then on the stack, we're only going to store the location of where to find that first element in the list in this heap. So we store our list in the heap, and on the stack, our variable list only stores the location. Where can I find that list in the heap? Because I know it's in the heap somewhere. I don't know where. Tell me where it is so I can go there and find it. Now when we update this value, we got X and Y on the stack, and we want to update the list. We're going to create a new list that goes in the heap. And now our list variable is going to store the location of the new beginning of that list, which can show us where the rest of it is. So we store the location of the list in this variable, which changes, but that location is the same size. It takes up the same amount of stack space. List is a variable that stores one location in the heap. And even though that location is changing, the amount of memory that that location takes up in this list variable does not. And then we can make our changes in the heap to this list and create new lists and update this list and just change the variable, which location this variable is storing. The colon is a prepend. So I'm taking this list that has 2, 3 and prepending 1 to the beginning of that list. And this creates a brand new list with the values 1, 2, 3. Since that creates a brand new list, I have to reassign it to my variable if I want lists to be storing that new list. We are getting, this example kind of motivated linked lists, but that's all I'm going to talk about linked lists. Then it's over. We'll talk about linked lists in detail way late in the semester. I just wanted to use a list to kind of motivate that lists are a pretty special data structure. The details we'll learn about later. So let's talk about the heap. The heap is very dynamic space, meaning that whenever we want heap space, we just ask the OS, our OS or our JVM. We'll ask the JVM. We'll ask the OS on our behalf, and but I'll usually say ask the OS just because I don't know. I think it sounds more fun. But we'll ask the OS for heap space whenever we need it. If we need some space for an object that we want to create, we're gonna say, hey, operating system, give me some heap space. Give me a chunk of that RAM. I need some more of that RAM stick. Thanks for the stack and all, but I really need something more for this new object that I'm creating. The OS will be like, yeah, sure, here's the memory that you asked for. You can have, you asked for 10 bytes of RAM space, so here you can have these 10 bytes of the RAM stick. Here you go, enjoy. We don't care where that memory is. It can be completely different, completely really far away from our stack. We don't care. This can actually change as well. Our objects can move around on the RAM stick as the JVM and the OS optimize things, optimize memory. We also don't care about that. We just care about using and get your shot glasses ready, using a reference to figure out where that object is in the heap. So we have a reference to that memory that was, and we use the word allocated. I'll probably use that word, but don't sweat it if you're tripped up on the vocab. We're going to have a reference to that memory in the heap, which we don't care where it is, but we want the instructions of where to find that memory. So our variables that store objects only store references to those objects, which are instructions of where to find that object in heap space. You're going to get sick of counting. I'm telling you, it's going to be, you might want to make over-under bets instead of just counting them all. The over-under bets will be more interesting. It's going to be a lot. So references are what's stored in your variables. Your variables never store an object directly unless it's one of those primitive types. If it's one of those int, double, long, etc., those ones from the slide. That was a comprehensive list. Anything else is not going to be stored in an object, or is not going to be stored in a variable. Variables of object types that are non-primitive types only store a reference to that object, which are the instructions of where to find it in the heap. This includes every single class that you'll ever write. Every single class that you create is going to be stored in the heap space, and variables of those types are only storing a reference to that object. This includes all the other classes, Jake has rating lecture with a party of 6. What's up? I don't know how to react to raise during a lecture. Welcome. So that data, those objects that you write are all storing references to those objects on the heap. And every class that's not one of those, that's a built-in Scala type, that's not one of those primitive types, is also going to be stored with just the reference to that object, and it's going to be stored in the heap. And the reference is going to tell us where to find those objects. I'm going to repeat that like 100 times because this is so important and to understand this pass-by reference. So whenever we have a variable that stores a reference, Whenever we assign that to another variable, that's going to only copy the reference. You're never copying an object whenever you assign a variable of type to a value of that same type. You're only copying the reference over. This is the same when we call methods. So if a method takes an object as a parameter, it doesn't actually take an object as a parameter. I'll always say that, and we can say that as kind of shorthand. But what it takes as its parameter is a reference to an object that's on the heap. So we don't like copy the entire object and all of its data and give that to the method. We just say, hey, method, here's where you can find this object in the heap. It's over on the heap. Here's the directions of where to find that thing. Go do your thing after that. That object can change, go to the heap and change that object's, I think I used the wrong word there. That method can follow that reference to the heap and make changes to the state of that object. And that change will be reflected after that stack frame is destroyed, which I'll talk about in a few slides. But first, that's a lot of abstract. That's a lot of theory and everything. Let's talk about an example and digest that information a little bit and talk about what's happening when we are creating new objects. So here's an example using our player class from Monday. And if you download the slides before lecture, I updated these like 10 minutes before lecture, so you can download the new slides and get this example. It was an item example before that. Whenever we create a new object, which we're going to call our player's constructor, which takes an XY location and max hit points, whenever we create that new object, the new keyword, what that's going to do is say, hey, operating system, I need some heap space. I got this object. It's going to be really great, but only one problem. I need some space. I need some of that juicy RAM. Give me some space to be able to store this thing. And new is going to ask for exactly enough space that we need, which is enough space for 2 doubles and an int. So we get that space. The operating system says, I got some space for you. Here's where that space is. It'll give us a reference to that memory address, the first address that we're allowed to access. So we can access that space, that heap space. And then we're going to go to that heap space, add our state variables to that heap, that space in memory, and then return a reference to that place in memory. So we went to that heap space, created the player, created variables X location, Y location, and max HP. And, actually 4 or 5 variables, right? I forgot we had other variables in this player class. Current HP and damage. Those will also be stored in that memory, in heap space in that memory. And then we get a reference to that location in memory. What's stored in player 1, the variable, is only the reference to player 1. Yeah, references are very much like pointers. When you get to 220 next semester, there will be a distinction between references and pointers. For Scala's purposes, we're only talking about references. And there are some caveats to it, like methods are actually passed by value, but the value is a reference. We can get into little minute details like that. For now, I'm just going to call them references flat out throughout everything. Next semester, pointers and references, the differences will be important to you. And Dr. Ethan Blanton will straighten you out on all that. So player 1 is the variable is only going to store a reference to this new object that was created. We created an object in the heap space, and player 1 stores a reference to that object. That's all it stores. It doesn't actually store the player object itself. It stores a reference to the object. With the counters going, I'm really conscious of how many times I say reference, but I can't get through this lecture without saying it like a billion times. Not literally a billion. That's not the over-under. So we can assign a new variable to, we've done assignment before, to player 1. When we do this assignment is by reference. So that's all player 1 is storing is a reference to an object that was created on the stack. On the heap. And when we say player 2 of type player equals player 1, remember player 2, a variable of a type of an object like this, what that variable stores is only a reference. It's not actually a player. It's just a reference to a player. So when we say player 2 equals player 1, this is an assignment by reference. Player 1 resolves to a reference, the location of this player that was created. Player 2 is assigned that same reference. So player 1 and player 2 are both referring to the same object. This is the same when a method's parameters are assigned to its arguments during a method call. When we create a new stack frame and we put the parameters on the stack and we assign them to the arguments of the method call. Same thing here, same exact thing as what's happening in this line. That's going to be something we call pass by reference. Technically pass by value, and the value is a reference. We're not going to get that picky about things today. So this is only an assignment by reference. We can use the dot operator to access an object that's stored on the heap. We go, what the dot says is, this is a reference. Dot says, I don't care about your reference. I care about what you refer to. The dot operator is going to travel to the heap and access the object that's being referred to. So now that we're at that object, now we can access its state and behavior. So now the object that's being referred to, this player that was created, we're going to call its move method, which takes a dx and a dy and moves this player's x and y location. We're going to move that player, access the stack access the heap where that player is located, and change its state variables. Since player 1 and player 2 refer to the same object, they're going to both see that change. And notably, this method call, this puts a new frame on the stack. We add variables to it. We create local variables. We do some computations. We change some things around. But this method returns unit. So when we talked about stack, after the stack frame ends and is removed from the stack, all the variables that were created in it are destroyed, and all that's left is its return value. Its return value is returned to the stack frame that called it, and that's the only thing that lives on from a stack frame, from its existence. Well, this method returns unit. So what the hell? Like, what do we get from this method call? We're not even assigning anything. We're not doing anything here. So why do we even do this? Because this method is going inside the stack frame. Some of the computation is escaping that stack frame, running over to the heap, making a change to the state of an object on the heap, then returning back to the stack frame, and then the stack frame is destroyed and returns nothing. But that change that was made on the heap persists. So even when a stack frame doesn't return anything, it can still change the state of the program by changing heap space, which does not get destroyed after stack frame is destroyed. Heap space can persist outside of stack frames. It exists, kind of independent of any stack frame. Heap is better than stack. Yeah, repetition. I mean, they work together to get the job done. And since player 1, I got ahead of my slides on this one, but since player 1 and player 2 refer to the same object, I say player 1 in this check player location, I say player dot access the object on the heap, check your X location, check your Y location. Well, the X and Y location are both referring to this player, which have been updated to 3 and 4. So both these variables both show location 3, 4 because they both refer to the same object. There's only one player object in this program, in this snippet of code. It's only one player object. We only called the keyword new once. So we only asked for heap space once. There's only one object in this program. So when we have two variables like this, and this is a good way to think about it in your quizzes, when you see a program like this, look for how many keywords new there are. How many times is new called? That's how many objects are on the heap. Unless I get tricky and do that in a loop and create a bunch of objects in a loop or something. However many times new is called, that's how many objects are in the heap. I have two variables, but only one new. These variables have to refer to the same object. There's really no other option unless I get really cute with things. Player 1 and player 2 both refer to this player, the only player in this program. Heap space does get destroyed when there are no reference. So I have an object on the heap. Does that count? I said half of the word. Does that count as one? I have an object in the heap, and I have references to that object on the stack. Once the stack no longer has any references to that object on it, so once all the variables that stored that reference either go out of scope or get reassigned, once that you can no longer access that heap object on the heap, then the JVM is going to do what's called garbage collection and destroy that, free up that heap space. But you'll never notice that in your code because it only happens when you literally can't ever access that again because you lost all the references to it. Once you don't have any references, it disappears, gets garbage collected out of existence. So we got till 220, right? Yeah. So let's digest this example a little bit before we go into the next one. I mean, yeah, you can access it because it's in your RAM. You could, there are ways. I mean, you can, run Linux and, rewrite the kernel, and yeah, you can access it. But through the JVM, through normal means, you can't. So the JVM frees up that memory. Yeah, exactly. What Y2NK4. For the heap, is it possible to delete or undo the new edits, or is it permanently? Yeah, it's permanent. It's permanent, baby. Like when this method makes changes to that object in the heap, like there's no Control Z for that. You can't undo that. You could undo it. You could say move -3, -4 if you want to undo that change, but you would have to do that manually, depending on what your program is doing. Yeah, when the stack and heap get disconnected, those heap objects, because the stack is really where your program's running. Once a heap object gets disconnected from the stack, it's a good way of thinking of it, that object is gone. It has a very dire fate once we no longer talk to it. Our program is the only entity in the universe that can access those heap objects. And once we can't access them anymore, once that program can't, then poor objects on the heap. The amount of new in the code is equal to the amount of objects in the heap. I'm hesitant to say yes because I'm sure there's some fancy way to not do that. But in general, the answer is yes. But the keyword new is not always in your code. For example, when we create a new list, we don't use the keyword new. I actually have that note right here. Like when we create a new list or map, we don't call the keyword new. But inside those map and list classes, those classes have methods that use the keyword new. So you won't always see the keyword new in your code. Yeah, if we created a new player right here, then player 1 and player 2 would each refer to different objects on the heap. And then they would behave independently of each other. Where do memory leaks come from in Java programs? If you keep storing the references, like if you have a big data structure of references to big objects on the heap, you could have a memory leak. But once you get rid of those references, memory leak's gone. In C++, in C, where you have to manage your own memory leaks are common. Again, got to sell 220. 220 is going to teach you all about that good stuff. You have a feeling you somewhat understand this? Nice. Yeah, check player. Oh, so we saw this last lecture, the check player location. It's in the repo. You can check it out. It just makes sure that this player has this XY location with asserts. All right, let's go. So we can only create objects when we go to test. Like when you're testing things, yeah, you would create an object and then have asserts based on the state of that object, access its state and behavior. on the heap. So let's go into another example. And just like last week when we were talking about stack, this is meant to be language agnostic. So we can focus on the concept of stack and heap memory and trek through the stack and heap as we're going through the execution of this program. Super simple program. Of course, reinforcing classes a little bit and things like that, but it doesn't really do anything. It adds 1 to 0 and prints 1 to the screen. In terms of functionality, not much going on here. But let's track through how this program is executed and what's going on in the stack and heap. Where first we have this new class. It has one state variable. It's initialized to 0. We have a main method, which is going to create an instance of that state. Call a method that takes that an object of this type as an input, accesses its state variable and modifies its state, and then returns nothing. And then we just print that state to the red panda. I'm so sad to hear that. Computer science it's the best thing ever. It should be for everyone. At least a little bit of computer science should be for everyone. I'll firmly agree with that. So let's take a look at stack and heap. Oh, I named them RAM and RAM. Damn it. This is the stack, and this is one chunk of heap space. And let's walk through this program. So the first thing we do, pour one out for Red Panda. It's hopefully they're just having a bad day, but we'll work with you if you're sticking with it, Red Panda. So we're going to create a new class, a new object using our class, and what that does is we're going to the OS and saying, yo, I need some memory. I need enough memory to store one int. Can you give me enough for that? And then any overhead that I need for the object. Operating system says, sure, here it is. We don't care where it is, where it's giving us this memory. We don't care where it is on our RAM. We just know that we have enough space for this object. So we create this object in the heap, and we get a reference. And I'm going to start using this @ symbol for references. I'm going to say roughly this is at memory address 387. It doesn't read exactly like that, but for our purposes, we're going to pretend this is directly the memory address. So at 387, that's the location of this object in the heap. And on our stack, we create a variable named data, which is going to store that reference at 387. This reference is referring to this memory address, which stores this object, which has a current state variable with a value 0. Then we're going to call this method. This method takes an object of our class with state type as a parameter, and that's going to be passed by reference. So when we say passed by reference, this is what we mean. The parameter is being assigned the argument just like any other method call, but the argument here is a reference. Data is storing a reference to an object on the heap. So input in this stack frame that's created is going to get that reference. So input is also referring to the memory address 387. And when we, inside this method call, we say 387, hey, at 387 or input dot statevar, let's go to this memory address that's stored at input, that reference, follow it to the heap using that reference at 387, go over to the heap. So at this point, we're in heap space. And then access the variable named statevar in this, kind of can be thought of as a different scope, the statevar in this object in the heap. Statevar had value 0. We're going to add 1 to that and reassign it. So we make this change in heap space or heap memory. Again, I use those interchangeably sometimes. I usually call it heap space normally. I should just update my slides to fit what I usually call it. And updates the value in this variable, and then the method returns. The method doesn't return anything. That stack frame's destroyed. The input variable that was storing the reference 387 is destroyed, but destroying that reference doesn't affect the object at all. We still have data with the same reference, referring to the same address in memory, referring to the same object. Now when we're back in the main method, we access data.stateVar. Data is storing the reference 387. Access that place in the heap. .stateVar, look for a variable named stateVar attached to this object. Its value is 1, so we print out 1. So even though this method call didn't return anything before its stack frame was destroyed, we still see the effect. This is what we call a side effect. This method, or function in this case, had a side effect of changing the state of an object that's on the heap. So we actually did get to see some change from a method that returned unit. So like when you're testing your objects, your classes, create objects of those types, call the methods, even though those methods return unit, those methods are going to the object in the heap, changing that object's state, and then you can check the state to make sure the state is what you expect it to be. Or in certain cases, like in Monday's lecture task, you would call a method that checks the state, and you have this intermediate state variable that you create and you name so you can't access it in your testing. I wonder if that's the problem, that Muffin Man, you were having. You can't access your state variable in your testing because I'm going to have a state variable in my code in Autolab too, but I'm going to name it something different than you have, most likely, more often than not. So you can't access that because then when your tests are ran against my code, things break. But you can, in that specific lecture task, call the scanned method, which updates the state variable, whatever you create and whatever you name, in the heap, and then you can call times scanned, which should return that variable, the value in that variable. Yeah, Friday's lecture is all about, so that's everything. I've said everything that I have to say about heap memory. Friday's lecture is all about reinforcing this with more examples, more and more examples. But I've said, like, the whole concept is out there, but it shouldn't really make sense yet. This is something that takes, it's fantastic if it does make sense to you. This is something that takes at least 2 lectures to really see what's even going on, and realistically longer than that to really get a good feel for stack and heap. You'll have to study and think about this one a bit. Stack and heap memory are tricky concepts. It just takes a while to think about. And then memory's freed up. End of the program. Since we reached the end of the program, everything on the stack is destroyed. Since that means we lose all references, everything in the heap's destroyed. Like, everything's just gone. Destroyed. And one thing I wanted to mention, stateVar here is an int, which is a primitive type, but it does actually get stored in the heap because it's part of an object that's stored in the heap. So there are ways to get primitive types in the heap. As long as they're part of an object, that entire object is stored in the heap. I've had that confusion in the past with students. Everything's destroyed, and we're back to the lecture task. And actually, we have a few minutes. I can go to IntelliJ. So back to the lecture task. Create a sale with %off. Apply that to sale testing items. Add sale has to take a reference to a sale. So add sale takes an object of type sale, but now we know that actually is just a reference to a sale, not an entire sale object. And you have to make sure you're handling your references properly. There is a test. There is an incorrect test case which does not handle references properly. So when it gets add sale called to it, it remembers the %off of each sale that it gets, but it doesn't store a reference to those sales that it gets. So if the sale price, the %off updates of that sale, that update is not reflected in the sale testing item. For your code, it has to be, and for your testing, you need to test for that to get full credit on lecture task 2. And sometimes I do give bonus slides that explain a little bit about it. I usually don't show them, but since this is the first one, I'll show it, where I kind of get you started a little bit on the lecture task, how to use this, how to set it up, how to write tests to test objects. We haven't really done this before, so I wanted to show the bonus slide. Let's head over to IntelliJ quickly. And not that one. Let's talk about the example that we saw. Oh, I did it in the test. And here's, I have this test the, oops, because I didn't pull. Oh my goodness, tell me I didn't push again. I didn't push. I pushed the new lecture slides, and I was thinking that was what I needed. It wasn't. So I have this new test case, brand new, just as of this second. So if you pull, you get this this example now. Playing with references, where it's an expanded version of the example that I showed in the slides. And what I want to do is, the thing we're going to do as often as I can find time to do, is set a breakpoint and run the debugger on this thing. So I'll run this in debug mode and take a look at everything that's going on in the stack and heap. So the debugger is still mostly going to show us the stack, but we can infer some things that are going on in the heap through the values that it's going to show. So we haven't done anything yet. Let's step through once and create a new player on the heap and assign player 1 the reference to that player. So we step into the constructor. Something I actually don't think I mentioned on Monday. When we call the constructor, any code that's outside of all the methods, that can be treated as initialization code. All of this code is going to be executed when the constructor is called. This is a bit different from other languages where you define an explicit constructor method. Things are a little more implicit in Scala. These are the constructor parameters, and then all this code is executed when the constructor is ran. So we get our x location, y location, max hit points, and then this code is executed. Max hit points, we're going to assign that to HP. Damage dealt, assign that to 4. And then return that player that we created. Store it in player 1. So if we look at the stack, we're in this, the only stack frame here, which since we're in Scala tests is, a little unreadable, this anonymous function, because we never named this function. We just called test and gave it a function, details. But we have on the stack, in scope currently, this object player 1. And we can see this it's at something 1839. We're going to pretend that this is a location in memory. It's a bit more convoluted than that. There's a lot of implementation details, the JVM and stuff like that. We're going to pretend that this is an address on the stack, or at least a reference. This is the reference for the player. Twitch froze for you? Looks good on my end. Yeah, looks good on my end. And player 1 is player 1. We can expand this. So this is saying we have a reference to something at 1839 in the heap, and we expand this to see all of the variables attached to this object in the heap. We can go through, step through this. We say player 2 equals player 1. And when we do that, we have player 2 on the stack also at 1838. So in the debugger, you can use this to tell that these two objects these two variables are referring to the same object. They'll have all identical state variables and values. And as we move through this program, player 2 moves. That's going to access its X location and Y location and update them. I'm inside a method call. So I'm going to have this, the keyword this, storing a reference to the calling object, which has all of my state variables, and dx, dy, the parameters for this method. I'm going to take one step through this, and we can see X location is updated to 3. And if I go to my top level stack frame, this stack frame is still executing, I can go up to my previous stack frame, And I can look at player 1, and I can see that change is already reflected in player 1 because they're both referring to the same object, this object that's at 1838 someplace in heap space. 1838 is kind of the location of where we can find the player object for this reference that's being stored in this variable. So we can see that player 1 already sees that change because there's no other choice for it. It's referring to the same player object. There's only one player object here. So they both see that change. And of course, after that stack frame returns, that stack frame's gone, all the local variables are gone, but player 1 and player 2, both referring to this object at 1838. And that object 1838 has a new X location and new Y location. Those changes were made on the heap through this method call. And then we can assert both of those tests pass. Player 2 is going to attack player 1. Well, we understand references, so we know that that player just attacked themselves 2 times. Player 1 HP, player 2 HP, both going to be 2. We're going to, oops, I didn't think that would went into the assert. We can assert all these things. They're both 2. We know that because we're looking at the stack. We're looking at memory. Player 2 is going to attack player 1 again. Well, we know that that's just player at 1838 attacking player at 1388. Attacked himself again, or herself. HP is -2, so these players are going to be... Oops, I wanted to go into conscious. These players are going to be unconscious. HP is less than 0. Oops. No, because the testing is over. And we can resume. Our test passes. Test pass.